In this video, we are going to discuss Chapter 6 Revision Quiz. So we have handpicked about 5 questions that you all requested me to discuss. So here we are discussing these questions one by one. So let's start with question 3. An AC voltage is connected to a resistor of resistance R. The mean power dissipated in the resistor is P. Okay, so you can see the AC voltage is only connected to a resistor. So this is a pure R circuit. And it say that the mean power, the average power dissipated, means by converted to another form. Okay, the average power used or the mean average power released in the resistor is P. Okay, so this P here is actually an average power dissipated. Okay, so if the same AC voltage is connected to a resistor or resistance R, so right now you keep the same AC voltage as the old situation just now, but you're replacing the resistor R with another resistor of resistance 2R. So you are doubling up the resistance. So if you double up the resistance, what happens to the mean power dissipated to the resistor? Does it increase? Does it double? Does it increase by 4 times? Does it half? Or it become a quarter of P? So this is what we want to investigate. Keep the same AC voltage, just change the resistor. Okay, so how are we going to go about this? We know that the relationship, we have to build an equation that describes the relationship between the mean power dissipated in the resistor and the AC voltage. So and the resistor as well. Okay, so these 3 things will have to be in the equation. Okay, because now they are saying that they are keeping the AC voltage the same voltage, but they are changing the resistance. So now they want you to investigate what happens to the mean power dissipated. So there are 3 variables here which we want to include in our equation. So this is a pure R circuit. For pure R circuit, you know that the mean power dissipated or the average power dissipated at the resistor will be P average equals to, I call it VRMS, RMS, IRMS. Okay, or you can call it V0 I0 over 2. Okay, both are the same actually. Okay, initially the equation should be VRMS IRMS cos phi, where the cos phi is the power factor. Okay, but if you remember, for pure R circuit, the phi will be equals to 0 because the V and I are in phase. So since cos phi and we took phi to be equal to 0, cos phi over here will immediately become 1. Cos 0 degree become 1. So our average power dissipated will be V0 I0 over 2. Okay, but this equation here only consists of 2 things that we discussed just now. It has the power, which is the first thing that we mentioned. It has the AC voltage, which is represented by the peak voltage over here. But this equation here lacks the resistance here. Okay, it lacks resistance, so we need to take out what we don't need. We don't want the current, so we want to take out the current and replace it with resistance instead. So we know that this is just what we know about pure R circuit. We know that pure R circuit V0 is equals to I0 R. So for this, we can change I0 to be as V0 over R. Okay, this is for pure R circuit. You understand this? This is similar to the Ohm's law that you learned in chapter 3, just that now the voltage and the current, they are varying sinusoidally and they are both in phase. Okay, so knowing that, you can change the equation a little bit. Place it with V0 over R, then you get V0 squared over 2R. So this is the equation that we are going to use because it consists of all 3 things that we mentioned just now. It has the mean power, it has the AC voltage represented by the voltage peak, it also has the resistance R over here. Okay, so this is the equation that we are going to use, and we are going to create an old case and a new case. So the old case will be just P average equals to V0 squared over 2R. Okay, the new situation, we put prime to every single variable. So the mean power will have a new mean power, so P average prime. We also have a new peak voltage, so the new peak voltage will be V0 prime. So you square it and divide by 2R, but now it will be a new resistance. Okay, so you want to find the relationship between the new resistance and the old resistance P. So you want to find whether the new you want to find the new mean power in terms of the old mean power. Like the new mean power is P average prime over here. You want to find P average prime is how many times of P average. So in order to do that, we have to compare these two equations. How do you compare them? By taking the new equation divide by the old equation. So if you do it like that, then you get V naught prime square over 2R square divide by V naught square divide by 2R. Okay, so this is the part where you need to understand the relationship between the old and new. Between the old and new, you know that the peak voltage never change because it's the same AC voltage. You are not changing AC voltage. So the original peak voltage will also be the same as the new peak voltage. So in that case, you can cancel this V out. Then the next thing that we know is that the new resistor is twice the value of the old resistor. So you can see that R prime, the new resistor, is equals to 2 times of the old resistance. Okay, so knowing that, we can continue to cut everything out. Actually, we can continue to cut 2 as well. Then you arrive at the equation which is R over R prime. And once you reach this step, you can sub in R prime to become equals to 2R. R prime is equals to 2R. So you get P average new divided by P average old is equals to half. Which therefore you know that P average new is equals to half of P average old. And P average old is just P as mentioned in the question over here. The original mean power dissipated is called P. So that's why the old P average here will be replaced by the symbol P. So you can see that the new average power, the new mean power dissipated at the resistor is half of the old mean power dissipated in the resistor. Okay, so this is how you solve through the ratio question. You figure out an equation that has most of the variables that you are going to manipulate or keep constant or respond. So once you get the equation, you create an old equation and a new equation and try to take the new to divide by the old. Once you do that, you see the relationship between the new V and the old V, take the relationship between the new R and the old R, and from there you find the ratio between the new mean power dissipated and the old mean power dissipated. Okay, so this question, the answer should be half P, and that's how we solve this question. Next. So a sinusoidal alternating voltage of period T is connected across a pure capacitor. Which of the following graph of power against time T for the capacitor? Okay, they are saying which power time graph is correct to describe the power across the pure capacitor. So how can we do this? Okay, so it's a pure C circuit because there's only one capacitor, no resistor, no inductor. So this is a pure C circuit. So you know that if you study the voltage and how it changes with time, probably not voltage first, let's start with current. Okay, let's say the current change with time in the sinusoidal fashion. Okay, this is the most common one. Okay, I is equals to I naught sine omega t. Okay, but you know that the V, the voltage across the capacitor, is going to lag the current by 90 degree. You know that V lags I by 90 degree or V lags I by pi over 2 for pure C circuit. That's why you see that for the graph of V, it will reach the peak later than the read peak. Okay, it will reach the trough also later. So if you draw the situation, it'll be something like this. Okay, so this will be V. Okay, so now we know that power is always taking the instantaneous V multiplying by the instantaneous I. This is an instantaneous power. So the power at any certain moment, you can determine it by taking the voltage at the specific moment multiplied by the current at that specific moment. Then you get the power at the specific moment. Okay, So what we're going to do is we're going to do it graphically. We're not going to multiply it using maths. We're going to multiply it graphically. Okay, to be more specific, I'm going to highlight a few features, but first let me draw the axis first. We know that this is power, this is against time. Okay, we know that there are a few points which will definitely be zero. Like let's say if the current is at the peak, the voltage is at zero. So because the voltage is at zero, no matter how big your current is, your power will be zero. So as long as you see zero for the green line and you see zero for the red line, those places will have zero power. Those moments will have zero power. Okay, so this moment should have zero power, 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 this moment should have zero power. Okay, so you can go down and draw the 9 lines by yourself. Okay. Okay, so now let's see. The the red color line, which is representing current. The current is at the positive region, whereas the voltage is at the negative region. So if you take negative V multiplied by positive I, you get a negative power. That means by it should be at the bottom region over here. Okay, follow up. This region over here, the green line is above, the red line is also above the time axis. That means that the V and the I are both positive, therefore the power should also be positive. So it should be here. Okay, then you know that once you cross this dot over here, you can see that the red line is now at below the time axis, whereas the green line is above the time axis. So they are at opposite side of the time axis. So that means the V is positive, the A is negative. So you get the V is positive, the I is negative, therefore you get a negative P. Okay, so you can work through it by yourself. You'll see that it alternates like this. Okay, so what can you say? You can say that the graph will look something like this. Okay, so if you notice over here, the period for one oscillation of current, is this much. This is the period. And you can check that for the voltage as well. The voltage also have the same amount for its period. But if you look at the power here, the power only takes up 2 columns only to finish one oscillation. This is the period for power. This is the period for voltage. This is the period for current. Therefore, you know that even though it's a sinusoidal shape, but period for power is half of period for V and I. That's why you should expect that if your voltage has a period of T, that means if your period of voltage is equals to T, and that means the period for power is equals to half of T. Okay, you can see that it's half. It's only taking up 2 columns, but voltage and current, they are taking up 4 columns. So the period for power is half of the period for voltage and current. That's why it's half T. Then this will be the period. So one complete oscillation will take half of the period for voltage to complete. That's why you can see that it needs to complete 2 oscillations only it reach the period of the voltage. You can put your half T over here. Then this is one single complete oscillation. So this is T power. The amount taken is half of T, which is half of T as we mentioned right now. So this will be the answer over here. Okay. Immediately you can say C and D is wrong because C and D here, the P average will not be equals to 0. The P average will not be equal to 0. It will be equals to somewhere near the middle. Be equals to somewhere near the middle. Okay, so if P average is not equals to 0, then it's very likely that it's a pure C or L or a RC or a RL or a RCL circuit. Okay, definitely not wait sorry. You see that the P average is not equal to 0, right? Immediately you know this is pure R circuit, sorry. Okay, sorry, brain not working. This must be pure R circuit. Or it must be a combination of either R and C or R and L or RCL circuit. Only you are able to have non-zero average power. So same for this situation, it can only be a pure R circuit, or it can be a pure RC. It can be an RC, or it can be an RL, or it can be an RCL circuit. Okay, so these two are not our answer because the average power is not equal to 0. Okay, you can just do your average by yourself. Looking at the graph, you know that the average is not at 0. The average is not at 0. Because the average is not at 0, right? That means the P average here, if the P average is not equal to 0, then you know that the VRMS, IRMS, cos phi will not be equal to 0. Therefore, you can know that phi is definitely not equals to cosine 0. Okay, therefore, you know that phi should definitely not be 90 degree, 270 degree, and so on. Okay, so because of that, you know that your voltage phasor cannot be perpendicular to your current phasor. Okay. So it cannot be a pure C circuit because pure C, the angle between them is 90 degree. But we see here, if you're using graph C and graph D, you cannot be 90 degree. But we know that for pure capacitor is 90 degree. So graph C and graph D are impossible. Okay. Yeah. Yeah, so definitely cannot be pure R, cannot be pure L. Cannot be pure R, cannot be pure L for graph C and graph D, because pure R and pure L, the phi will be 90 degree, then your average power will be equal to 0, which is not the case for graph C and graph D. So our question here give a pure C circuit, so definitely pure C circuit, the average power should be equal to 0, because 90 degree, you get average power equals to 0. So if you can look here, you can eliminate C and D, only left with A and B. Because A and B, they both average to 0. But now you have to look at the period. You've already mentioned the period for a period for power is always half the period of voltage. That's why you have two complete oscillation within the period for the voltage. Okay, this is how we think about the question. Sorry if I didn't manage to explain it really coherently. Okay, next question. An incandescent light bulb is connected to an AC power supply. What happened to the flow of current and voltage across the bulb? Well, it's just that you have a you have a AC power supply, accumulator, and you connect it to a incandescent light bulb. So incandescent light bulb is those like traditional kind of light bulb. Okay, the one that you see with filament inside, those are incandescent light bulb. So because incandescent light bulb, how it works, right, is when you have current flowing through. Okay, when you have current flowing through and the filament has high resistance, so a lot of energy will be dissipated at the incandescent light bulb. Okay, filament, high resistance. Okay, so you have greater energy dissipated. Because you have greater energy dissipated at the filament, what will happen is you heat up the filament. So heat up the filament until a certain temperature. What will happen is it will glow. Then that's how you light up a bulb, an incandescent light bulb. So the main feature of an incandescent light bulb is it must have high resistance. Only you have a lot of energy dissipated at the filament. You need to have high resistance. Only the charges will give a lot of energy to the wire when it pass through the incandescent light bulb. Okay, you need to have high resistance over here. So the most important property of the filament here is it has high resistance. So the resistance is the main property of an incandescent light bulb. So you can think of it as a resistor is connected to an AC power supply. So you can think of it as a pure R circuit. Okay, a resistor, because an incandescent light bulb works by having high resistance. So you can think of it as a resistor connected to an AC power supply. What happened to the flow of current and voltage? You'll know that if it's a resistor connected to an AC power supply, it's a pure R circuit. Pure R circuit, the voltage and the current will be in phase. That's why the answer will be A. Okay, if it's leading the current, then this is pure L. If current is leading the voltage, that means voltage is lagging behind, and this is pure C. Okay, but we have mentioned just now, the main thing is the filament has high resistance. So the resistive property is the main issue over here. The resistive property, high resistance. That's why I think of it as a pure R circuit. Okay, so let's move on to the next question. In which of the following does the value of power factor can be maximum? Okay, again, let's revise what is power factor. You learn that power, the mean power dissipated, can be determined using VRMS, IRMS, cos phi. Okay, this is for a combination of RC or L in the circuit. Okay, it's general. If you have more than one, if it's not a pure R, pure C, and pure L, then you have to use this to determine the average power. Okay, so it's a combination of R, C, and or L. Okay, so if you want your power factor to be maximum, this is the power factor. So power factor maximum means by when power factor is maximum, and what will happen is the maximum of cos phi is 1. And therefore you can know from there that it will be inverse cosine of 1. Inverse cosine of 1 will be pi over 2, will be cosine of 1. Oh, will be 0, sorry. It will be 0, will be 2 pi, will be 4 pi, so on, so on. Okay, so knowing that, we know that our angle for phi here must be either 0 or 360, and so on, so on. So what does it mean is, if you want your cos phi to be maximum, your phi should be equals to 0 degree. So phi equals to 0 degree can appear in the phasor diagram if your current is pointing in this direction and you want your phase angle to be 0, then that means your voltage phasor will have to be in the same direction. Okay, voltage phasor have to be in the same direction. Then only the phi will be equals to 0. But if that is the case, right, then what kind of situation will give you I and V not aligned? Well, it's a pure R circuit that gives you this kind of phasor diagram, right? So it's a circuit contains an ideal resistance only. Okay, if it contains ideal inductance, then the voltage will be pointing upwards. If it's containing an ideal capacitance, it will be pointing downwards. But now we want the angle, the phi, to be equal to 0. We want the current and the voltage to be pointing in the same direction. And that only happens when you have a pure R circuit or when you have an RCL circuit in resonance. If you have an RCL circuit in resonance, then the XC and the XL will cancel each other out. Then your impedance will just be pointing towards the direction of current. Okay, so this is how you solve this question. Let's move on to the last one. Alternating current cannot be measured by a DC ammeter. Well, because the average value for AC for complete cycle is 0. Okay, if you are having an AC current flowing in the circuit, then the current will be changing with time, something like this. Okay, so if you take an average of this graph, you can see that the upper area will cancel out the lower area. So at the end, you take an average, the current will be equals to 0. That's why your DC ammeter will measure nothing. You cannot measure the alternating current because the average value of the AC current will be equals to 0. And that is what the DC ammeter can pick up. Okay, so that's it for this question 22. And I believe that's the last question for chapter 6 revision quiz. So that's all for this video. Thank you very much.